Hello everybody, I welcome you all to NCAS Geology class. In last classes we have discussed about different physical properties of minerals, and today I will discuss about some of the properties that I have not discussed, that I will discuss now. Let me discuss luster. Now, what is luster? Luster is the appearance of a mineral surface in reflected light, or how the reflection takes place over the mineral surfaces. That is described in terms of luster, or it is, we can say, it is the shining property of the minerals. The luster that we perceive on looking at a macroscopic specimen is principally the result of amount of light reflected from the surface of the mineral and scattering of light from the surface, and that also takes place internally, and the amount of light absorbed by the mineral. These factors, they control how much will be the reflection, how much will be the scattering of light, on the basis of which the different terms are used to describe luster. The figure below relates the different types of luster possessed by minerals, and there are three major varieties of luster which is increasing, which are in increasing order of light transmission. Opaque. In opaque, the transmission is nil, we can say. Translucent, to some extent. Transparent, light is fully transmitted. So, the opaque, translucent, transparent terms are based upon the light transmission capacity of the minerals. And if we see that the light transmission is found from metallic to submetallic, then to dull, here transmission gradually decreases. Vitreous, subvitreous gradually decreases. And how the surface appears, accordingly various terms are being used. Vitreous, it is the luster of broken glass. To less extent, there is subvitreous, and this light transmission, light reflection capacity will be described as silky or pearly, satiny, waxy, or greasy, resinous, depending upon the scattering of light, depending upon the light that is being absorbed, depending upon the light that is being reflected. And adamantine luster is the luster where there is maximum light scattering, or it is brilliant luster. The minerals which show adamantine luster are generally the gemstones. Gemstones, they show adamantine luster. So, as you go down in this series, we see that the luster gradually diminishes. Finally, we get dull or earthy luster, and if we take into account the coherence of light reflection, so in dull there is no coherent light reflection. As you go up gradually, we see that some amount of coherent light reflection and much coherent light reflection takes place in case of metallic and adamantine luster. And similarly, in this direction from opaque to translucent transparent light transmission increases, and from non-coherent light reflection to much coherent light reflection begins from dull luster to submetallic luster, metal luster and adamantine luster. Similarly, from RD to subvitreous luster such as silky, pearly, satiny, waxy, greasy, resinous luster to vitreous lusters. So, these are the different terms which are being used to describe the shining property of the minerals. So, luster is broadly divided into metallic and non-metallic lusters. In case of metal luster, the luster is described for the metals, and these are generally opaque minerals, and the light shines when it falls over the metallic surfaces. So, their face surfaces show bright luster. For example, silver, brass, chrome, galena, magnetite. These are opaque minerals no doubt, but when the light falls over the face surfaces, it is highly found to be reflected. So, their shining capacity is very high, particularly in case of metals. And in submetal luster, it results from large amount of scattering of light or from mineral not quite opaque. Non-metallic minerals are not opaque. So they are not quite opaque, and in that case large amount of scattering of light takes place. For example, chromite, magnetite, bornite. Chromite, mineral of chromium, mineral of iron, mineral of, so these are the metallic minerals we can say. So here they show submetal luster, then dull are the luster. Some opaque minerals reflect little or no coherent light and thus appears duller are the kaolinite, nitre. So these are this is kaolin clay mineral. These minerals, they are more or less earthy. So they do not reflect the light in that manner, so that it can be described as presenting dull luster. Then in case of non-metal lusters, we have the vitreous luster, resinous waxy luster, pearly luster, greasy luster. If we take into account the luster of vitreous, if we consider vitreous luster, the luster is the luster of broken glass. For example, quartz, tourmaline, if they are broken and light is reflected from their broken surfaces, that luster, that shining property is described as vitreous luster. It is the, in case of resinous or waxy luster, it appears in case of resin, in case of sphalerite, in case of sulfur, resin like luster. Similarly, pearls, seashells, the surface appears, this type of luster appears parallel to cleavage surfaces, as we see in case of muscovite, talc, apophyllite. That cleavage surfaces show shining luster, and that shining luster is described as pearly. Greasy luster, it appears as if it is covered by a thin layer of oil, as we see in case of nepheline, chlorite, milky quartz. And this type of luster show play of colors similar to oil on water, greasy luster, oily luster. And when it is silky luster, it shows surface that appears to be silky, filled with fine fibers. surface of silk or surface of gypsum, satin spar. Satin spar is fibrous. So, similarly, chrysotile asbestos. So, asbestos provides fibers, silky fibers. So, the fibers, they provide silky luster. Oily substances, they provide greasy luster. Cleavage surfaces provide pearly luster. Resin provides resinous luster. Adamantine, it is bright, shiny, brilliant appearance of minerals with high refractive index, as we see in case of diamond, cerussite. Cerussite is the carbonate of Pb, sulfate of Pb, such as anglesite. So, this is in case of adamantine luster, the luster is highly brilliant. So, these are the terms: vitreous, resinous, pearly, greasy, silky, adamantine. These are non-metallic lusters. In metallic luster, we will find the luster of metals, metallic, submetallic, dull in case of earthy minerals, clay minerals, and much coherent light reflection takes place in case of metal lusters or in case of adamantine, in case of minerals which are highly brilliant showing adamantine luster. There is much coherent light reflection, and if we take into account increasing light transmission, it begins from opaque minerals to highly transmission capacity in case of transparent minerals such as quartz or rock crystal, which is highly transparent. Similarly, Iceland spar in case of calcite, it is highly transparent. So, these are the terms which are described in luster, and let me discuss the other properties. Let us say that is diaphanity or opacity. Opaque, transparent, translucent. Whether light is fully passing through the mineral or it is being obstructed by the mineral. Based upon that, the light transmission capacity of minerals is being studied. They are described as opaque, transparent, translucent. These are the terms. So, they are the terms of diaphanity or opacity. It is the light transmitting capacity of the minerals. The minerals that do not transmit light, they are called opaque. These minerals have dark grey or black streaked metallic minerals. The minerals that transmit a significant portion of incident light are described as transparent, such as quartz, calcite. Analogous to glass windows, as objects can be seen through the glass window. Thin sections are found to be more transparent compared to thicker sections. The minerals which are transparent generally produce white streak. The minerals that transmit some light but not enough to transmit an image are described as translucent. Their streak may be white or colored but not grey or black. In case of grey and black, it is opaque. So, gypsum, we can say it is a translucent mineral. So, these are the terms which are based upon light transmission capacity of the minerals. They are opaque, transparent and translucent. Now, let us discuss what is specific gravity or density of the minerals, because that is also one important factor. If you see quartz is very light, but similar looking mineral is Pb sulfate. which is having same color like that of quartz, but its specific gravity is very high. Similarly, if we compare magnetite, chromite, they appear to be heavy. So, they are having high density. So, density sometimes plays a role in identification of the minerals. As we see quartz and barite. Barite is heavy, barium sulfate, and chromite, magnetite, they are iron and chromium bearing minerals. So, let us discuss how density plays a role in identification of minerals, or what is density. Density is the mass per unit volume of the material. The unit is kg per meter cube or gram per centimeter cube. The density of a mineral is proportional to the number of atoms per unit volume, which is called as the packing index, and to their atomic mass number. Minerals with very high density, say gold, they tend to have crystal structures with very closely packed spaced atoms. Many atoms per unit volume, that is close packing, that are very high atomic mass numbers. For example, gold, it is having the mass number 197. The minerals with low density such as ice tend to have crystal structures with widely spaced atoms. Atoms are widely spaced. But when we talk about closely spaced structure, mostly face centered cubic, very closely spaced. So, here density will be high, here density will be low. That means few atoms per volume, that will give rise to low density, low atomic mass, low mass number, hydrogen 1, oxygen 16. So water is having low density. Specific gravity is a dimensionless quantity, because it is described as density of mineral by density of water. This is a comparison, that is why it becomes dimensionless. It is defined as the ratio of the weight of the substance to the weight of the equal volume of water at 4 degrees centigrade, which is temperature coincident with the maximum density of water. And thus, density of a mineral is described as the density of the, or specific gravity of mineral is described as density of the mineral by density of water, which is equal to 1. So, specific gravity of a mineral depends upon the kind of atoms that make a substance, the manner in which the atoms are packed, the structures remaining same, but the minerals having heavier elements or having higher atomic weights are having higher density or higher specific gravity compared to those which are made up of elements having lower mass. So, let us see this example. Structure is orthorhombic. We have the aragonite, strontianite, witherite and cerussite. All are having same structure, but their composition is different. Calcium carbonate, strontium carbonate, barium carbonate, Pb carbonate. So, Pb is having higher atomic weight. Calcium has lower atomic weight. That is why its specific weight is 2.94, whereas Pb having 6.58 because of the higher atomic mass of Pb. So, all are carbonates, all are having same atomic packing, but because of this heavy element Pb, cerussite is having higher specific gravity than aragonite. Minerals having solid solution relations show continuous change of specific gravity. For example, phosphorite 3.3, but phyllite is 4.4. So, phosphorite to phyllite, they form the olivine group of rocks linked through solid solution type of reaction. So, minerals displaying polymorphism, this specific gravity is controlled by the packing of atoms. For example, graphite, hexagonal packing, low packing, hardness specific 2.23. But when we talk about diamond, it is cubic packing, tightly packed, density becomes specific becomes 3.5. Minerals can be assessed by lifting with regard to their specific gravity, just by in hand. When we lift the mineral, on that basis we can sense through our senses which mineral is heavy, which mineral is light. As I have already discussed, quartz and barite, Euxite is 1.96, very light, barite 4.5 appears very heavy. If you look at barite and quartz, they will appear like similar, but barite, if we lift it in hand, it appears to be very heavy. The average specific gravity of silicates is varying from 2.65 to 2.75, quartz 2.65, feldspar 2.65, 2.6 to 2.75, calcite 2.72. Metallic minerals have average specific gravity equal to 5, that is equal to pyrite. Silver 10.5, graphite 2.23, very light because it is a non-metallic mineral. Measurement of specific gravity. How can we measure the specific gravity? Specific gravity can be measured by Joule balance or by heavy liquids. Heavy liquid may be bromoform or methyl iodide. The mineral whose specific gravity is to be determined, that should be studied by pouring the mineral powder into these heavy liquids. Heavy liquids are maintained in different densities and the density of liquids are known, the density of minerals are not known, and when the powders are being poured over the denser liquid, the mineral powder which is light, that will float, and accordingly we can compare the density of the mineral with that of the heavy liquid, and accordingly we will say what is the density of the mineral. And by mixing acetone with the heavy liquid, we can dilute. Acetone is having density 0.79. We can mix acetone gradually with a bromoform or methyl iodide, and media of different values of specific gravity can be created. This value is quickly measured by Westphal balance. So, how a mixture of mineral can be separated? On the basis of specific gravity, let us have a mixture of quartz 2.65, tourmaline 3.2 and garnet 4.25. This is a mixture of quartz, tourmaline and garnet. The bromoform, if the mixture is added with quartz, it floats on it, as bromoform has specifically 2.89, quartz having 2.65. So, quartz can be separated well from the surface of the bromoform liquid. Now, in order to separate the two other from each other, the heavy media is to be prepared by mixing acetone with bromoform till the heavy medium becomes heavier than tourmaline, that is specified 3.2, and less heavier than garnet 4.25. So, in this way heavy medium is being prepared, tourmaline floats and garnet sinks to the bottom, and thus they can be separated from each other. So, heavy medium, the density or specific gravity of heavy medium is being controlled by gradual addition of this acetone. The specific gravity can also be determined by use of small bottle called pycnometer for powdered minerals. Now, let me discuss some other properties such as magnetism. There are some minerals which are highly magnetic, there are some minerals which are susceptible to magnetism, and accordingly we have diamagnetic minerals, paramagnetic minerals and ferromagnetic minerals or ferrimagnetic minerals. Ferromagnetic minerals are highly magnetic and paramagnetic minerals are weakly attracted towards magnet, and diamagnetic they are non-magnetic, not attracted to magnet. They are repelled by magnets. Pure feldspars, halite, quartz, these are diamagnetic. Paramagnetic, impure feldspars contain iron, garnet, hornblende, many pyroxenes because they are iron bearing minerals. And when you talk about ferromagnetic, they are highly magnetic, as we see in case of magnetite. So, magnetism for long periods of time is retained by the minerals such as magnetite, which is highly magnetic, pyrrhotite, highly magnetic, and natural magnets such as lodestone or magnetite. These are lodestone. These are natural magnets, or the ferromagnetic minerals can be magnetized by using these natural magnets. So, on the basis of magnetism, we have three types of minerals: magnetic, ferromagnetic, paramagnetic, and diamagnetic. Diamagnetic are non-magnetic, whereas paramagnetic and ferromagnetic, they can feebly magnetic, and ferromagnetic minerals are highly magnetic. Highly magnetic minerals are magnetite, pyrrhotite, and lodestone. Then let us discuss what is mineral property, what is electrical property. Some minerals may conduct electricity through them. The electrical conduction occurs when the mineral's electrons can move throughout the structure, such as is the case with minerals with metallic bonds. In metals, the electrons they can flow. They contain 3 electrons. That's why they are conducting, such as copper. Some amount of electrical conduction occurs in minerals with defects or imperfections. Imperfection in the structure and in bonding, as we see in case of graphite. Graphite is conducting. Graphite is a mineral rich in carbon. Because of its hexagonal packing, it becomes conducting. Carbon atoms uses its 3 electrons for strong covalent bond, sigma bond, in one plane, and the 4th electron or valence electron is not used in bonding. It becomes free to move within the layers and thus helps in electrical conduction. Some minerals become conducting for electricity when they are subjected to increase in temperature. This is called pyroelectricity. Pyro means fire. When they are subject to heating, they becomes conducting, such as tourmaline, topaz. Similarly, there are some minerals which become conducting on application of stress or pressure. This is piezoelectric property, as we find in case of quartz. This is quartz. So, quartz is showing piezoelectric property. Tourmaline, it is showing pyroelectric property. Both the piezoelectric and pyroelectric properties are the characteristics of anisotropy minerals that lack center of symmetry. So, this causes one end of the mineral to differ from the other end of the minerals, allowing electrical potential to be created across their ends, and the minerals thus become conducting. When one end of the tourmaline is heated, it becomes positively charged and the other end becomes negatively charged. When cooled, charge reverses in the ends. So, in this manner, these minerals become conducting. Then let us discuss what is radioactivity. We know there are certain minerals which are noted for their emission of alpha, beta and gamma radiations. Particularly minerals having atomic number more than 82, that is Pb, lead, they are generally found to be radioactive. These elements they emit alpha, beta, gamma radiations which affect photographic plates. These elements are called radioactive elements and the minerals which contain them are called as radioactive minerals. The presence of radioactive elements are detected by Geiger counter or scintillometer or scintillation counter. or by gold leaf electroscope. The radioactive elements are uranium 238, uranium 235, thorium 232, potassium 40, then argon 40, rubidium 87. So, these are radioactive elements and they are being used to, or the minerals which contain these radioactive elements, they are being detected by these instruments, counter, gold leaf electroscope, scintillometer. These are the instruments which detect the alpha, beta, gamma radiations, and the radioactive elements, they continuously go on emitting alpha, beta and gamma radiations. So, the minerals which contain these elements, they continuously emit radiations and these radiations are being detected by these instruments. So, now let us discuss some other properties such as taste, odor and feel. Taste: some minerals are noted for their taste, on the basis of which they can be identified. For example, halite, it is salt, salty; sylvite, it is bitter; borax, it is alkaline; borax, potash, soda, they are alkaline; H2SO4, acid, sour; nitre appears to be cooling; green vitriol, it is astringent; the sharp, dry, puckering taste like unripe banana; strong tea, which is called astringent. It helps in skin care, helps in reducing bleeding, green vitriol. So, these are some of the minerals that is noted, identified on the basis of the taste, then on the basis of the odor. Some minerals are noted for their typical odor: native sulfur, marcasite, sphalerite, they produce sulfur smell when crushed or when they are powdered, sulfurous smell. Arsenopyrite, real gar, they give rise to garlic smell, or they are said to be alliaceous, garlic smell. Arsenopyrite and real gar, mineral of sulfur, real gar. Quartz, limestones, on heating or rubbing, they provide rotten egg smell, that is foetid smell. Clay minerals, they give rise to argillaceous smell or clayey smell. Then let us discuss what is feel. Certain minerals are noted for their feel, how we feel. When you touch these minerals, how we feel. We may feel greasy, we may feel soapy, we may feel rough surface, we may feel harsh surface of the minerals. Soapy generally kaolin, rough surface is bauxite. So, talc, graphite, molybdenite, they appear to be greasy due to their van der Waals bonding. Certain minerals, they adhere to tongue. They are kaolinite, clay mineral, montmorillonite, clay mineral, because they are fine grained clay, that is why they stick to tongue. So, in this manner, by their greasy feel, soapy feel, rough feel, harsh feel, the minerals can be identified. Then characters depending upon heat, that is fusibility. It is taste of how readily a mineral melts or fuses under the influence of heat. It is tested by blowpipe analysis. Von Kobel have given a scale of 6 minerals in which temperature fusion increases by somewhat equal steps. That is called Von Kobel scale. The minerals are stibnite, which easily becomes fusible having MP melting point 525 degree centigrade. As you go down, stibnite scale, fusibility scale is 1, followed by natrolite scale 2, almandine garnet scale 3, actinolite scale 4, orthoclase scale 5 and bronzite scale 6, and gradually the temperature increases. In case of stibnite, the melting temperature is 525 degrees centigrade. In case of natrolite, it is 965 degrees centigrade. In case of almandine, it is 1050 degrees centigrade. In case of actinolite, 1200 degrees centigrade. In case of orthoclase, 1300 degrees centigrade. Bronzite, it can be hardly be fusible in ordinary blowpipe because its melting temperature is around 1400 degree centigrade. So, as you go down in the scale from stibnite to bronzite, the temperature of fusion increases. The fusion property is used in identification of certain minerals. These minerals, these are the which can be fused easily by blowpipe, by allowing the heat through blowpipe to fall over these minerals. By that process, we can get them fused. So, this is the scale given by von Kobel, fusibility scale, and through this we can identify these minerals: stibnite, natrolite, almandine, garnet, actinolite, orthoclase, bronzite. They can be easily identified on the basis of their fusion temperature. So, this is all about the physical property of minerals that I wanted to discuss, and I think I have covered all the properties, and I thank you all for giving a patient hearing to my talk. Thank you.